Hi, in this video we're going to look at how matrix equations where a matrix times a vector equals another vector relate to the span of vectors. So here's this important fact. Given a matrix A and a vector B, the equation AX equals B is consistent if and only if B is in the span of the columns of A. To see why this is true, we can take the fact AX equals B is consistent and rewrite it using the definition of AX, which is just a linear combination of the columns of A written as vectors using the entries in X as weights. And consistent just means that it has a solution vector X, that there exist numbers for x1 through xn that make it true. In other words, saying that AX equals B is consistent means that B is a linear combination of the columns of A, which means that B is in the span of those column vectors. Because the definition of the span is just the set of all linear combinations of those vectors. If these last two steps here aren't making sense, you should probably go back and review the video from the other day, titled Geometry of Linear Systems, The Span, which went into more detail about the definition of the span and how it relates to solutions of vector equations. Here's an example that shows what this looks like. If you want to try it yourself, now's your chance to pause it. To solve it, we can write the left side as a linear combination, x1 times v1 plus x2 times v2. Then you can write this vector equation as a system of equations like so. And then write the augmented matrix so that we can row reduce it, because the reduced row echelon version will tell us the number of solutions. By the way, if you understand what you're doing, you can skip a few of these steps and just go straight to writing the augmented matrix. That's what most people do in practice. I'm writing it all out here because it's important for everyone to understand why these different equations, these different kinds of notation are equivalent. Then we can row reduce this matrix. Let's make the upper left 1 here a pivot, and starting with two row replacement operations, you can get rid of the -1 and the -3 below. That will be row 1 plus row 2 to replace row 2, and 3 times row 1 plus row 3 to replace row 3. Then, the leading 1 in row 2 will be the next pivot. So let's do row replacement operations to make the entries above and below it a 0. That will be -2 times row 2 plus row 1 to replace row 1, and -4 times row 2 plus row 3 to replace row 3. This gives a reduced row echelon matrix, which we can then write in standard notation as x1 equals -3, x2 equals 4, and 0 equals 0. So the solution of the system is -3, 4. The vector equation and the original matrix equation are just different ways of writing the system, so the solution vector for the original matrix equation is the vector -3, 4. And yes, it's consistent. This means that B can be written as a linear combination of v1 and v2, which means B is in the span of the two vectors. To see what this looks like geometrically, this green plane here is a picture of the span of v1 and v2. So v1 and v2 are definitely on that plane because v1 is equal to 1 times v1 plus 0 times v2, and that counts as a linear combination of them. And so is v2 here. And from this angle, it's hard to see if B is part of this plane or not, because we've got a two-dimensional screen here and we can't really see all of it at once. But if you turn it to the side, there, yeah, you can tell that it looks like B is on that plane. And yeah, here, if we draw a picture of -3 times v1, it looks like that. And then if we add 4 times v2 to that vector, it looks like this. And yeah, that gives you B. For the second problem here, let's skip some steps and go straight to the augmented matrix. Doing the exact same row operations as before will put the matrix in row echelon form, but the last equation here is 0 equals 2, which is always false no matter what x1 and x2 are, so the whole thing has no solution, and the answer is no. You can see that in the picture, C is not in the span of v1 and v2. Now, let's look at a more abstract example, and I should say this kind of problem is extremely important for linear algebra, so you should probably pay attention. Here, we're given a matrix with 3 column vectors, and looking at statement 2, we want to know if this matrix equation is consistent, just like in the previous example. But this time, we're not just talking about one equation with one specific vector b, we want to know if ax equals b is consistent for every vector b with 3 entries. So we're really talking about an infinite number of equations because there's an infinite number of R3 vectors you could pick. We want to know if every single one of those infinite number of vector equations is consistent. And looking at statement 3, we want to know if the span of the columns of A is all of R3. In other words, if you take any vector b in R3, then b is in the span of the column vectors of A. And I rewrote the statement this way so you can see that statements 2 and 3 are really just saying the same thing with different notation. Because for any particular vector b, ax equals b is consistent if and only if b is in the span of the columns of A. So we just want to know if that's true for every vector b in R3 or not. All right, let's work on A here. We want to know if A has a pivot in every row. So we need to get it in echelon form to see where the pivots are. And to do that, we're going to do regular old row reduction. So I'm going to make a pivot in this upper left position here. And you can do row 1 plus row 2 to get a new row 2 to cancel out this negative 1. And then negative row 1 plus row 3 to get a new row 3. And that should give you something like this. So you can see that the pivot positions are not in every row. It only has 2 of them. So whatever that has to do with these others two, we know that this statement is now false. For number 2 here, if we want to show that something is true or false for every vector b in R3, we can't assume anything about the entries in B. So we just know that we have 3 different numbers, 3 different real numbers. So we can give them a name, or 3 names rather. Let's call them B1, B2, and B3. So that's B, and any vector b in R3 can be written like that. And so the ax equals b equation then we could write as an augmented matrix with the b's on the other side. And then we could row reduce this using the exact same steps we did before. So we did, because the A, we still want to get the A part on the left here into echelon form. So we're still going to have a pivot here. We're going to do row 1 plus row 2 to get a new row 2. I'll leave row 1 alone for now. But when we do this row operation, we have to keep track of the b's as well. Oops, that's supposed to be b1. So we're going to do b2 plus b1 here. And then for the last one, we're still going to have 0, 0, 0 here when we do negative row 1 plus row 3 to get the new row 3. But now we're going to have b3 minus b1 here. Now let's see how having a row without a pivot position in A here affects this last equation. Because you end up with this being equivalent to this equation 0 equals b3 minus b1, this equation could be consistent or it might be inconsistent. It depends on what the b1 and b3 vectors are. So for example, if the b vector is 7, 4, 7, then b3 minus b1 is just going to be 0, and this last equation here is just going to be 0 equals 0. Which is okay. But if you have b1 and b3 not equal to each other, then b3 minus b1 becomes something not 0. So this last equation becomes 0 equals 5, which makes the whole thing have no solution. So To answer the question, is AX equals B consistent for every vector B in R3? No. For example, this one. And statement 3 is false for the same reason, because statements 2 and statement 3 are really just saying the same thing. If you were going to do statement 3 on its own without doing statement 2 first, you'd say B is in the span of these three vectors. You'd say, is it possible to write B as a linear combination of those three vectors? You'd end up with a system of equations that you could write as an augmented matrix like this. So the moral of the story here is that having a row in A without a pivot position can make it so your augmented matrix for AX equals B can have something 0 equals 5 or something like that. So it might be inconsistent, but it might also be consistent depending on what vector B is on the other side there. Here's another example, this time for you to do on your own. This problem is exactly the same as the other one, it's just that the matrix is called C instead of A, so you've got a different letter there. Also, one number is changed as well. There was a 1 here before, but now it's a 0. So that will change some things. So give it your best shot. Here's the time to pause it because the answers will appear in a moment. So these are all true. For C, I did row 1 plus row 2 to make a new row 2 to clear out that negative 1 there. And that gives you the 0, 0, 1 row. And then I did a row swap to get this 1 in that position and then that negative 2 in this position. And then a scaling by negative 1/2 on that negative 2 row. And then you can do a row replacement with that row to get rid of this negative 2 above. So it does have a pivot position in every row. So what does that have to do with 2 and 3? Well, if you make the augmented matrix for the Cx equals B equation here, and you do the same row reduction steps, just keeping track of what you're doing to the B1, B2, and B3 as you go, then you'll see that, yes, you do get a solution here for x1, x2, and x3 in terms of B1, B2, and B3. And we know that it doesn't really matter what the B's are, because having a 1 in every row means that there cannot be any equation in the form like 0 equals 5 or 0 equals 2 or anything like that, because all of the pivots mean you're going to have a variable on the left of each side of each equation. Now, I chose these two examples to try to convince you that for any particular matrix, A or C or whatever, these three statements are equivalent. They're either all true or they're all false. We're going to write down this fact as a theorem, which I'm not going to formally prove here because I think the explanations for the last examples justify it well enough. I should say, though, that this theorem is really important. You know how in calculus classes you use the chain rule in most of your homework assignments because calculus is full of derivatives to do and the chain rule is just really useful for doing derivatives? Well, this theorem is kind of like the chain rule for linear algebra. Linear algebra is not so much about calculating things as much as calculus is, but it's more about knowing things. And if you know that one of these facts is true for a particular matrix A, then you know that the other statements are true as well. And if you know that one of them is false, then you know that the other two statements are false too. So using this theorem to make some kind of conclusion about a matrix will be an important step in a lot of the problems in this class. So your exercise now is to pause the video, read the theorem, and convince yourself that it's true. You don't have to write anything down for part A. Then pretend that your friend understands why statements 1 and 2 are equivalent, but they don't understand what the pivots have to do with it. Write down a few sentences to try to explain to your friend why statement 3 is on the list in your own words.